analysis, and more. Coming to the actual usage of Ansys, it is used in multiple fields such as academia, aerospace and defense, automotive energy, healthcare, oil and gas, and whatnot. Today, we have Mr. Hemant Fegade sir as our guest speaker, who will discuss and throw his lights on the topic CFD analysis of a heat sink with Ansys. Before asking him to start this session, I would like to make all the participants familiar with Mr. Hemant Fegade sir's background. Mr. Hemant Fegade sir, presently a research associate in Elite Techno Groups, has a rich experience of having worked on CAD modeling for 3 years. His area of expertise consists of CFD turbomachinery applications, heat transfer applications, and CAD softwares like CATIA, Creo, and Ansys Workbench. He has also worked on CFD simulations, IC cooling simulations, centrifugal pump analysis, valve analysis, and propeller of a drone. Not only this, he has also helped 1,000+ students to learn concepts on design and enlightened them to become industry ready. Currently, he is working on completing the Masters at Vishwakarma Institute of Technology, Pune, in the field of heat power engineering. With this, I would like to invite Mr. Hemant Fegade sir and welcome him on behalf of the Mechanical Engineering Society. Good evening, sir.
Yeah, hi. Am I audible?
Yes, sir, you are very audible.
Yes, sir, you are audible.
Okay. Thank you for the great introduction. So yeah, and thank you all for joining with this session. Shall we start?
So before we start, let me introduce some of the rules that participants must follow during this session. Number one, we request all the participants to maintain decorum during the workshop, or else you might be removed from the meeting. Number two, for any queries, questions, you can use the chat box. We will answer all the questions at the end of this session. Number three, an attendance form will be provided for this before the session ends. For getting certificates, you all must fill out that form carefully. Lastly, there will be an announcement for an exciting event with prizes worth more than 40,000. So we request everyone to wait until the end of the workshop. Sir, please, now you may carry on.
Great. Let me begin by sharing my screen and just a minute. Yeah, is my screen visible?
Yes, sir.
Yes, sir.
So, hello participants, we are going to discuss about heatsink analysis, and in this basically we are going to discuss about types of sink and the most in-demand heatsink configuration. Then we'll discuss about how to define the problem and simulation requirements, and basically the usual process of Ansys, how it works, what are the different modules covered in Ansys, and like CAD cleanup, meshing, post-processing, and essentially we are going to see how the concept relates to the simulation and how we can extract results from that. Okay. Now, before all of this, let me just ask you one question: why electronics need cooling? So, can anybody in the chat post what they think? Why do electronics need cooling? It's okay. I would like this session to be interactive. So if you can post any questions, any answers to this question, that would be welcome. Or I am anyways going to continue. Okay. So essentially, why do electronics need cooling is because the first thing that comes to mind when electronics, right? When electronics function, they function on electricity. With the components, the design and the chips that are going to be designed, right? In those, there is going to be to a certain extent, the electrical current is going to move through those components. Now, the biggest issue is the components sizes, right? They are very small. So considering those sizes and considering the considering the overall like working of those components, there is a lot of there is not much space, if you can consider, for the electrons to move throughout the system. So basically, if I tell you this, like there is a very limited opportunity for more and more electrons to go through or move through this constrained space of the due to the constraint of sizing, right? Now, due to that, there is a limit to which a particular component can be functioned. And due to the constant electricity flowing through these components, heat is being generated because the materials, because we need to limit the voltage that is going through that particular system, right? And the reason is because there are certain thermal limitations, or basically there are certain working operation limitations on that material at that particular size, that they do not permit us to have high voltages going through throughout the systems. And essentially, because if you are working with the usual power that we have, like 230 volts, that is running through our homes and electronics, right? So there is always adapters and all those situations installed to drop the voltage, right? The main reason is to induce the resistance, because if we don't induce the resistance, we because the voltage at which the overall operations are going to be will overshoot the operations, and basically it will melt down the components. That's why the that's how severe the electronics cooling is concerned. So the biggest effect of that is basically we need to limit the voltage. Now, even after we limit the voltage, there is certain amount of electricity moving through, and there is certain amount of heat being expelled. Basically, the electrical energy is getting converted into the thermal energy by significant impact due to the moving through the resistor. So just to show you, just a second. Yeah. So let's consider, excuse me for my drawing skills. Let's consider this is a resistor, okay? And this is a LED. Okay. Now, through this resistor, we need to pass the voltage. This is connected to a battery. Okay. Now, through these resistor, we need to move the electric current in order to induce the resistance, so that the LED can operate, so that the inner wiring of the LED doesn't melt away, right? Now, when your electrons are moving through these system, right, what will happen is there are going to be certain restrictions placed in this resistor, and they are going to be they will be largely impacting with each other. They will be colliding with each other, which essentially converts their energy into heat energy. And that's how resistors, and that's how all the electronic components emit heat. And that's why electronics need cooling. And essentially, the effect of this is basically it's so severe that even if you consider like a simple, like a general operation of a resistor or of a MOSFET in your CPU, it at a room temperature, if it's working at for about like 5 or 10 minutes, it generates like around 46-47 degrees Celsius of heat. And that sort of heat is very dangerous. Like prolonged exposure to that sort of heat is very dangerous, considering the amount of damage it's going to do to those components. And due to that, we need to install some cooling systems. We need to install some ideologies with this, and due to which essentially how we have these kinds of like components called as heat sinks, or liquid cooling systems, fan cooling systems, right? So those sort of systems you might have seen in your PCs or CPUs, even in laptops. So there are these fans installed for cooling purposes. So that way it's inducing forced convection, and that way they are being cooled. So one such component is a heat sink. Now let's see what a heat sink is. It's a device designed for dissipating heat generated by a miniature component to achieve cooler ambient temperature. So basically we are limiting the temperature within the certain limits to ensure its optimum performance. Now, when we are this is the general configuration of the heatsink. This is how it looks, and you must have seen this in your PC's motherboard chips, right? So there are with each of these chips and MOSFET and stuff like that, there is associated as heatsink. This is its only purpose is to just take away the heat from the component, like convect it away, and overall, like a fan or with the help of a fan or blower, the ambient air or ambient temperature air is blown over these heat sink to cool it off. So basically it's a device to dissipate the heat that is being generated constantly in order to maintain the temperature of the operating components. And we need to be we need to have the temperature monitored or regulated. Now the cooling principle is simple. You must have read through these convection cooling, right? Newton's law of cooling. So basically, using forced convection, air is basically forced on over the heatsink with a fan or a blower, and it's the velocity of the fan depends on the conditions how we are going to see this. Okay, so essentially, when it comes to heatsink and when it comes to such kind of requirements, right, analysis or any kind of a thing, like considering this, we cannot manufacture, like let's see, if I want to design a heatsink, I have constructed a heatsink, and I have no means to analyze, I have no means to know what sort of performance is going to do. Otherwise, by doing experiments itself, I need to be I need to assure myself, considering what sort of conditions are there, right? Now, with this, what happens is I need to create the prototype over and over again and construct the overall setup and like redo these calculations, redo these designs. With each improvement in design, I need to recreate, remanufacture and stuff like that. Like all of these is associated, right? So this is kind of an experimental way or a traditional way researchers used to do things. Researchers used to experiment, and they need to understand what sort of velocity is going to have an effect on the heat sink, and what sort of what sort of temperatures we are getting with certain velocity. So considering that, it was a very lot. It was a very time consuming section. It was very costly also. Now there is a one solution for all of this. That's called CFD. Okay, so it's called its full form is basically computational fluid dynamics, and it's a method which is a branch of fluid mechanics which deal with numerical data and numerical algorithms which which is used to analyze and solve problems which are involving fluid flows. Now, when we talk about a heat sink, we have a setup which is a heat sink is installed, and air is blown over that heat sink, right? So we need to have this sort of setup on a virtual space. So that's what CFD is, and that's to facilitate that virtual space, we have softwares like Ansys, like for instance. And apart from that, we do have other tools as well, so to operate with. With that, CFD is basically used for simulating any kind of real fluid systems, right? You use it for wherever there is a fluid flow, or turbo machinery applications, for aerospace applications, for hurricanes, wind predictions, for environmental studies, all of those. So wherever there is a fluid, any sort of fluid is involved, there is a need for CFD, because essentially when the industry standpoint is basically when you need to manufacture a new product, you need to evolve from your base design, right? Whatever previous product you were selling, considering that as a base design, whatever newer modifications in that design are being made, considering those modifications, you need to move further with that. And this is an easy way where we can simulate this sort of modified designs before manufacturing, right? So that is the biggest advantage we have, because with in numerous simulations, without wasting any manufacturing resources, without wasting any there is some sort of cost involved with this CFD as well, but it's not as severe as compared to the manufacturing and retesting, creating an experimental setup, complete lab for a single prototype to analyze. Now, due to this, what happens is basically you will get by conducting in-numerous simulations, you will get a general idea, you will get a precise idea of what sort of velocities you will be working with, what sort of temperatures you will be getting at the end of it, and are they optimum temperatures. And based on that, like, there are plethora of different sort of analysis apart from CFD. So there is a thermal structural analysis which is being done on heat sink, which is basically to analyze or gauge the structural integrity of a heat sink. Apart from that, there is also this computational fluid dynamics involved, where it is mostly focused on how the air is going to, based on the air flow, how the temperature is going to differ on the surface of the heat sink. It's called as a fluid structure interaction. In that also, like, there is like at a different level of fluid structure interaction kind of a simulation is being done. So this is going to be a that sort of analysis where we would be able to see how like a certain amount of air we are going to blow over this the heat sink, and how it is going to be like facilitated throughout the Ansys, right? Just that is the base idea. Now, CFD is made possible due to advancements in computers and their improved computational capability. So as I said, these softwares called Ansys, and like these are the tools which provide us the ability or computational power to solve and to basically simulate this. Now, there are three main modules in CFD. One is pre-processing. Okay, so pre-processing is basically, it involves geometry repair, creation, or cleanup. In simple terms, it's called cleanup. And second is meshing. So let's talk about geometry making and its constraints for a bit, right? So to simulate the fluid field, we need a negative volume. That means essentially what you need is, you need, if you are going to simulate, so let me just give a context to this, okay? When you are trying to simulate a system, consider this in terms of thermodynamics, systems and surroundings, right? So when you're simulating a system, you need to consider a domain, which is in which you are going to simulate a particular, like, in which you are going to have your system. So instead of imagining the, let me give you a better example, okay? So imagine your computer PC is open, and with that your fan is situated right next to your heatsink. Okay, so in this way, so this is your heatsink, and this is your fan just blowing air over that heatsink, right? So basically, I want to simulate this part. I want to imagine that this part is being this is basically all my system is, right? Air is coming from this pod and it's going over, and that's the all my system is. So you need to constrain the system into a box shaped, or any kind of shape you like, but it's generally using a cuboid shape, or like rectangular cuboid shape basically. So that is called as a domain. So where we are constraining our system into a finite space in a virtual realm or in a virtual platform. Okay, now that, with that ideology, that domain that we have constructed, apart from the components like the heat sink, and these are the components of the system, apart from that, whatever the volume that remains, it's called as negative volume. That is basically like air is going to flow over, right? So basically your fluid is going to move around in that negative volume. So that negative volume we need to create, and that is called as geometry making. So it's also involved in geometry repair, and repair and cleanup we'll see. I'll probably better able to explain it to you through the actual simulation, so that it will be much better over there. Now the context is something like this. Okay, now there are two kinds of fluid flows that we do. One is the internal fluid flow and external fluid flow, right? So the kind of fluid flow that we are talking about right now is external fluid flow, because we are blowing air over the heat sink, right? Now in similar cases, if you want to simulate a ship, right, or a submarine, right, so it is going to be surrounded by fluid. So in both cases it is surrounded by fluid, because with your ship, it's going to, the fluid is going to be air, and with submarine, your fluid is going to be water. It's still surrounded by fluid. That's the important point. Now, when you're simulating external volume, to reduce the computational cost and to reduce the general idea, because let me talk about the computational cost at a later part. Okay, at this point, just consider this as your system. This is how you're going to manufacture, or this is how you're going to model or use the existing model into repairing and preparing for the simulation. Basically, this gives us a constrained finite space in which we are simulating the overall flow and considering it as a complete system. There will be inlet involved, there will be outlet for the fluid to be flowing over. So simply put, here, if my ship is going in this direction, right, from, let me just use pen. Yeah, if my ship is moving in this direction, right, so my air, the air is going to be blown over the ship in this direction, right? And this makes this particular surface inlet to that particular case, and this is going to be the outlet. This face is going to be the outlet, because this is a constrained space that we are simulating. Nothing beyond that. Okay, so this is where your air is going to start coming in. This is where your air is going to start going out. Now, this is how any kind of external flow or any kind of a simulation is set up, or basically imagined or idealized. Now, there is also other thing that I mentioned called as internal flow, right? So I am not sure. Let me just minimize this. Yeah. Yeah. So just a minute. Yeah, never mind. Basically, this is another way of simulating a fluid flow. Basically, you are simulating internal fluid flow, right? So the fluid flow that we have seen over here is external fluid flow. Now this is an internal fluid flow. This is a turbocharger as you are seeing over here. Let me just show it to you. So when you have internal components that are moving by with the help of a fluid, like in a centrifugal pump, there is a volute casing involved, there is an impeller involved, right? This is rotating due to the fluid action. Now, as the impeller is rotating due to the fluid action, we need to also see the effect, because impeller is going to be a part of the effect that is being caused by the fluid motion. That is why we have basically we will be including that into the internal flow like regime, or basically we are going to consider the surrounding casing as its enclosure or as its domain. Basically, we are going to limit that part over there. So the essentially when we are constructing a geometry, when we are preparing a particular simulation, all of these factors we need to understand and consider before actually going into the simulation. The reason is because once you have a clear understanding of what you need to simulate, like what sort of system you would want in your simulation, then only you will have a clear understanding of how you're going to simulate it or what setup conditions you will be using. So I'll be talking more about that as I move ahead. Okay. Now, second step is a generating mesh. So mesh is nothing but discretization. So discretization meaning it's going to divide a particular geometrical model into small elements. Okay. It's similar to finite element analysis. If you might have heard about it, I am not sure. Okay, so the only difference in the mesh generation is it's controlled and more focused on important regions to improve computation time and achieve accuracy. Now, let me explain what all these factors mean. Okay, so essentially, what will happen is here you will have me just minimize this for a second. Yeah. Here, what we'll have is basically this this particular model, or this is kind of a 2D geometrical model that is being used for further explanation, because it's simpler to understand the mesh concept or meshing concept with a 2D geometry. Then we essentially are going to see the implications of a mesh in a more 3D environment space when we move on to the simulation. Okay. Now, consider this is your model where you are going to simulate your flow from over the car over here. That's this car profile is mentioned over here, and essentially, let me just do this. Yeah, essentially, uh, when we are going to use this is your geometry, right? And when it's going to be meshed, or when it's going to be divided into small particles, small elements, not particles, it's going to be looking like this. So why is there a need of dividing a particular model into small elements, right? Because when you are going to solve, right, when you are going to go for analysis, that means you are going to solve these variables using computers, right? So when you are doing this, the usual way, the analytical ways, the more traditional way, the way you solve problems using your like pen and paper. So those sort of calculations, you use integrations, derivations to solve these partial differential equations that defines these variables, like pressure, velocity, etc. And that gives you a conclusive answer of what that particular system's output is, what that particular system's like heat generation, etc. things are, right? Now, imagine these calculations being done by a supercomputer, or by a much better calculator, like much advanced calculator. It's that's there is to it, like the end line or bottom line for Ansys is it's a fancy calculator which actually solves these partial differential equations. And for it to be able to solve it within the required time, we need to divide that model into small elements. So what we will it will do two things. Basically, when you divide a particular model into these small squares, all of the properties that of the fluid that is moving past this point, because if in this case the air is going to be blown over from this part, so this line is going to be its inlet, this line is going to be its outlet, right? So your air is moving in this direction. Now it is going to go through this element, it's going to go through this element, it's going to go through this element. And with each element, you would get the exact amount, like you will get the value of velocity, pressure, temperature, density. So all of these properties, you will get those values of all of these properties throughout for each and every element. So that's why the finer or the smaller the size is, the better the accuracy is. The reason is you're going to solve, or CFD software, it is going to solve with a numerical methods, with the help of general numerical methods which are based on approximations and calculations, right? So whenever there are approximations involved, there is error involved. Now, the bigger the size of these elements are, the worse is your accuracy. Reason is simple, because it's going to be averaged over this element, because all of the properties are going to be averaged over this component, and there is going to be initial guesses involved for each of the velocities and etc. things that are going to be calculated, or the considerations that are going to be there. Based on that, the amount of like computational power or solving power or a better numerical method, because there are always flaws involved in numerical methods. That's why it's called as approximations. And due to that, we will have a lesser accuracy. That's why when we have smaller size of element, basically your equation is going to be converged at a better rate. So to explain this concept to you, so let's consider a graph. Okay, this is the graph. Okay, now if I solve, if I have to calculate the area under this curve, right, I need to be integrating this. If I calculate the area under the curve using an equation, it's really impossible for me to solve, because it's a very complicated curve, first of all. So similar concept is here, because the terms like the pressure, density, etc. things, these equations that defines these terms, if we compute it, if we map it in a graphical manner, there are going to be much more complicated curves as you go ahead. And when you are going to solve for those equations, you need to so basically, if I consider a very small amount of this curve, right? So it's going to be a very infinitesimally small, so that it's almost looking like a straight line. And due to that straight line, it's easier for me to calculate the area under the curve, because it's a rectangle, because I know the height, I know the amount of thickness that I have computed or considered, and it will be easier for me to calculate in this manner as compared to the overall area, right? Let's consider this, use this analogy for calculation. So this is the same analogy is used for finite element analysis, and CFD is nothing but a derivative of finite element analysis. So essentially, when you're talking about solutions, the smaller the element size is, the better it is for converging, the better it is for calculating the solution, right? So basically, smaller the size, you get more accuracy as with that. But there are other factors are involved also. Those factors are computational time and computational cost. Now the amount of time it's going to take to solve infinitesimally small element or infinitesimally small element, all these properties is going to be much larger as compared to solving on a bigger element. So because there is a lot of computation involved, because you are not only just reducing the size, you are improving the order of these equations, because all of these properties are going to be defined by partial differential equations, and there are going to be higher order terms like cubic term or fourth order term, fifth order term, so a squared, cubic, fifth order. So that's how the order of the equations, or that's how these properties are going to be defined. So you must have heard of Taylor series or those Fourier series, right? So those series are being used to identify the values, and this is why we need to we need to limit those values in those equations. Like we need to limit it up to a certain term to get to a certain accuracy. That's how the accuracy term is defined. This is done, the limitation is done because we need to improve, we need to gauge on the accuracy, we need to actually find a balance between computational cost and accuracy. So we cannot we won't be going for a more accurate solution if we don't need that solution. If there is no need, why should I invest a more computational cost? Because usually when you have, if I give you an example, okay, if I give you an example, if there are 20 lakh cells involved in a simulation, or let's consider like a bit more, 40 lakh cells involved in a single simulation, and if you have a PC that has 64 cores, okay, consider this is on a different level. So consider this a computational source kind of a way, because 64 cores, usually we have like 4 cores or 5 cores kind of thing, considering our processors are laptop processor or computer processors are considering that those cores are being if you have like 64 core PC, it's going to take it's still going to take two whole days, like 48 hours to complete the simulation for 40 lakh cells. 2 whole days, I'm saying, like non-stop the computer will be running for 48 hours non-stop, and it will generate some accurate, like some insane accurate results. So for an academic level or for a research level, that sort of level of analysis is not needed. And if and I'm talking about if using 64 cores, if generally we have in our laptops are like 4, 6, maybe 8 cores, considering the laptop range being like around 60 70,000 rupees. So that's how expensive it is to simulate at a higher cost. So that's why we need to find a balance between accuracy and computational time. That's why there is this concentrated mesh generation is introduced, where when we are going to solve for analysis in this particular analysis, it is more focused on the boundary region of the car, because we are more interested in what happens when the flow is moving past the car, what sort of drag it's generating, and all those things are more mattering over the surface of the, or near the surface of the car, as compared to over here. That's why we have a concentrated mesh around the car as compared to the other region that we have defined. The other region is defined because of certain constraints of the physics, so that we will have a certain space of simulation, because until and unless we have that sort of domain or that domain size defined, we won't get accurate solutions. So do that. So it's a concept called it's involving upstream flows and downstream flows as well. And this is considering the fluid flows. Like essentially we need to get the fluid at a stable state, at a steady state, when it's moving over something or something like that. So all of those parameters considered, we have the upstream and downstream, we have the domain size constraint to that. Now that involves pre-processing, right? Now whatever the solution part that I was talking about, that comes in the solving part. When we are going for this, right, when we are discussing, or when we are going for, once the pre-processing is done, once basically we have separated, or we have divided or model into small elements. Now next what? Now we need to set up the physics and for the solution calculation basically. So how are we going to set up the physics? So here we need to apply boundary conditions to the meshed models. So the boundary conditions that I mentioned initially, the boundary conditions are basically your inlet boundary, outlet boundary, wall boundary, surface of the component that you are going to simulate for. Basically whatever your physical components are there, and whatever the walls of the systems are, those are defined essentially to constrain the system, to complete the system, to make it realizable, right? Now to define this in a way where it involves this today's application called heat sink. So basically you are going to constrain your heat sink, it's going to be there, air is going to flow over that heat sink, and it's constrained in a dabba, in a domain, right? So essentially when your air is when that heat sink, the overall surface of the heat sink is going to be a wall, because it's going to generate some sort of heat, it's going to be a wall. So if it's generating heat, we need to give it a heat source. So that is a boundary condition. When you're talking about walls, when you're talking about inlet, outlet, at inlet you need to give velocity, because your air is going to move at that velocity from the inlet. So that velocity is carried, that velocity is a inlet condition. You need to also define pressure conditions. So because without pressure your flow won't happen, your flow won't be there. So essentially all of these parameters are well thought forward with, and then only you apply these boundary conditions to the model to mimic the real life condition, right? So there are like additional conditions, considering flow to be turbulent, adding gravity, also considering the flow to be multi-phase, or if there are more fluids involved than one, then that also comes in picture, where there will be multiple inlet ports through which different sort of fluids come in, they get mixed together. So these kinds of things we will be able to simulate. So that's how flexible computational fluid dynamics is. Now, essentially,
Sir has left. He might join in few seconds. Until then, please, if you have any queries, you can write in the chat box.
I guess there is a technical glitch. Thank you for having patience.
Hello, hello, am I audible?
Yes, sir.
Yes, sir, you are
Yes,
audible.
sir.
Hello,
Yes, sir, you are audible.
I'm unable to hear you all.
Sir, you can rejoin.
Am
Sir, you're not clearly audible, sir.
I'm clearly audible, right?
Yes, sir. Now you're,
Oh,
now you're
okay. Okay, I actually had some issues with my system, so I'll be resuming the session. Okay, I really apologize for that. Just give me a second. Yeah. So essentially, what we were discussing about, yeah. So when we talk about setting up physics and applying materials, etc. So essentially, we are setting up the overall case for the simulation. So in this case, we will be setting up for temperature simulation, where we will be setting up initial velocity conditions for the air. We'll be setting up pressure conditions at the outlet. Then there will be temperature conditions, certain heat source terms involved, where the chip is going to generate the heat. So there will be heat generation defined a certain amount, and then that heat generation is going to be slowly propagated through the heat sink. So conduction is also going to be defined over there via system coupling. So I will show you how all of those things are done. So essentially, we need to define every step of the way how the real system is going to look like in a virtual world, and that way we will get the outputs accordingly. So it's it depends on the analyst who is going to set up the physics. That depends on the, like, basically the output is going to be depending upon the analyst. So the better proficiency you have over these concepts and tool, because here in these analysis tools, it's not just the concepts are the tool is not just important, but the concepts are also very much important. How the back end functions of those of using these numerical methods and stuff like that, to understand their applicability in a certain situation, so that we can have more accurate, less time consuming solution towards the end of your simulation. Now, I was talking about these extra conditions like flow to be turbulent, adding gravity, will be more speaking over specifically more in that session. Okay. Now, last part is solving, right? Solution calculation. So essentially, these computational fluid dynamics is having a set of equations called as Navier-Stokes equations. Those equations are basically your governing equations. Those equations are being applied to the model when you are going for the setup, or essentially those equations are going to be solved using the solver that is being used. Now when we are going to solve for these solutions, right, when you are going to use these equations, they are being converted first into the linear algebraic form, then they are being fed to the software in an Jacobian matrix way. So basically, a matrix formulation is being done at the back end of the algorithm, and that matrix formulation is being fed to the simulation data, or wherever the setup is stored. That's how these equations are being applied, and essentially all is there in the backend programming of the Ansys tool. But to understand the applicability of each and every application of equations, how they are associated whether those equations are accurately representing the simulation, the kind of simulation that I wish to have. So those sort of things, those sort of ideology and mindset one must have to solve for further. So with this also there is a convergence criteria. Convergence is basically meaning that when you are going to solve for the analysis, right? Basically, I'll just explain more about convergence in the setup itself. So so all of these, once you're while once you are done doing setup and all of these things are done, you will be starting to calculate. You'll be just clicking calculate button. It will be starting calculating iterations, and it will give you a result of after the end of iterations. Right? Now with that, you can have your results and post processing. So last part about the last module of CFD is post processing. So in results, basically what you will do is you will include these reading value parameters. Like you basically you will be able to view what sort of pressure, velocity, density terms look like, or how they behave in certain regions of the simulation that you have set up. So to show you over here, the overall fluid flow simulation or the velocity. This is basically a velocity contour. It's called as a velocity contour or velocity streamlines, basically. So these velocity streamlines are showing over here that here you have a like moderate level velocity, which is moving at a steady state. Here you will have like blue. Basically, blue means the stagnant velocity, and as your basically blue is the lowest velocity and red is the highest. So that's how the color scheme or color code works in CFD, where you'll be able to actually identify the regions where a particular property is concentrated around. So basically here you can see over here, you will have a higher velocity because your air is going to be bouncing or like jumping off of this particular surface, like kind of a push up to that air. That's how this region is kind of reddish as compared to the other region. So these are the things that you will be able to identify, you'll be able to understand from results, and this is how you are going to get a general idea of how it's moving. And then there is called as a post-processing analysis using graphs and stuff like that to have conclusive data to back your simulation up, to understand the exact what solution you were expecting, whether the solution was in that particular range or not. So all of these things come under that. Now let's quickly talk about the simulation setup that we are having. Basically, where we okay, so basically when you're talking about a simulation setup over here, you will use the model called K epsilon scalable function. Materials are fluid. Fluid basically is defined as air. Solid is aluminum because the heat sink is going to be made up of aluminum. Heat generation at this is going to be defined at 15,000 watts per meter cube. The inlet velocity of the air is going to be considered at 0.75 meters per second at 282 kelvins. I'll be showing all the significances of all of these terms, what they are. And then we'll be talking more about like then the outlet pressure condition, which is basically we are going to keep it as default. Okay. Now, quickly, let me just yeah, let me just show you this Ansys video. Let me just share my screen once again. Now it must be visible. So it's very like RAM consuming, considering where we are showing these concepts, right? When simultaneously opening Ansys with presenting your screen and stuff like that. So that's why I have recorded a video for you all to, and based on this video, I'll be explaining further how the overall setup is being done and what Ansys is look like and stuff like that. Okay, so this is basically your Ansys GUI, Ansys Workbench GUI. Okay. Now over here at the left, you will see Toolbox. Here you have project schematic. In left in Toolbox, you'll have different analysis systems. So ANSYS doesn't only support the computational dynamics, but it also supports structural analysis. So based on the type of analysis, you can choose the type of analysis from here. Based on the simulation requirement, you can choose the type of analysis from here, and to simulate your conditions. So basically, you'll have your fluid flow. In that, you have fluid flow CFX and fluid flow fluid. For fluid flow CFX, it is more prominently used for moving parts. So whenever there is a lobe pump or a kind of centrifugal pump impeller movements are there, we use fluid flow fluid because there are going to be moving parts involved like fans and etc. So whenever there is a rotation or some kind of a thing, moving parts involved, which is influenced by the fluid flow, CFX is a better like alternative for fluid. All of those like conditions or all of those flows we can also do with a fluid flow fluent, but essentially there is a lot of what we can say a lot you should understand and you should know while simulating for the fluid, right? But while simulating the flow, a lot of considerations are being made in fluid as compared to CFX in that term. So there is all sorts of interfaces and etc. things are being involved. So all of those things will have there. Okay. Now we will basically drag the fluid flow fluent, left click, drag and drop it over here. Okay. So that creates a standalone system in your project schematic. So basically, you're seeing the loading time it takes to to even just to drag and drop over here. So that sort of heavy these softwares are. That's why we need to also take care of the computational time, and it's also a resource in this case. Now, basically, we will be importing a geometry. Basically, we'll be importing the geometry from. Let me just show you over here. Just let me just back it up a bit. Yeah. When you go to the geometry and right click, right, you will have an option for new geometry. You'll have an option for import geometry. For those who want to create the geometry, they use new geometry. And essentially, I have created the geometry in itself because I wanted to explain it in this manner itself. But if you have already, in general, what happens is for a simulation engineer never designs a geometry. Simulation engineer is being provided with the existing geometry from the design team. So basically in industry, there are different teams working in different domains, right? In OEMs, what happens is like original manufacturing companies, what happens is you'll have a design team that will give you the designed model or CAD model file converted into a .stp format. That model you're going to import, and that model you're going to simplify for your simulation. So that sort of thing happens when you are going for this. But for considering the overall explanation, we can just go with the new geometry, and having to skip all those things like considering geometry and all, I have just imported this setup. Okay. Now, as you can see over here, this is the setup where this is the heat sink, and the enclosure around this is a fluid domain in which the fluid is going to move forward. And there are three parts over here. So one is not visible at this moment. The chip that is being insulated or being, sorry about that. Basically, your chip is going to be installed below the heat sink. That is where your chip is going to generate the heat, and it's going to convey the heat to the heat sink, and the heat sink is going to convey the heat to the surrounding domain that we have established. Okay. Now, when we are here, first what we need to do is when importing this is a solid geometry for first of all. Okay, so you need to perform some Boolean operations in order to first separate these models into separate sections basically. So as you can see over here, there is three sections at the top at the left part. Let's pause it for a second. Yeah, over here you can see the chip, heat sink, and a fluid domain. So these are the three main parts of your simulation that are going to be involved. Okay. Now you need to first perform a Boolean operation or to separate the chip and the heat sink from the fluid domain, so that your fluid domain is actually going to be only associated with fluid, and heat sink and chip are only associated with solid. So that's how you are going to separate these, and that's how you are going to establish that this is a particular solid I'm simulating, this is a particular fluid that I'm simulating, right? And here you can see the small circular like section has been made at over here. This is going to be the actual inlet through which the air is going to go over. So instead of a fan, we can also simplify the simulation further by excluding the moving parts, where we can consider that air is casually moving over this heat sink, and it is coming from this particular hole or a circle, right? That's moving forward. Okay. Now we are here. I'm just creating the Boolean operation. Basically, what will happen is, just back it up a bit. So essentially, when I'm trying to create a Boolean, I will first go to create. I'll go to Boolean, and I'll just there are all sorts of operations in Boolean, right? So there is unite, subtract. So essentially, we want to subtract these two bodies from each other. And there is also a provision in this where we can preserve tool bodies. Basically, that means that we get to preserve the bodies that are going to be subtracted from this. So essentially, we would want to preserve the bodies because this is going to be a fluid and solid interaction. So what we want to do is we want to yes, just let me just forward it a bit. So basically, what we want to do is we want to have our heat sink, and as you can see over here, right? So we want to have our heat sink and your fluid domain separated. So when I hide the heat sink, because here you see the green tick, the green tick is green means that your fluid domain is only part is showing, and whenever there is a like basically hide operation has been performed over here, right click hide. So when you hide this, you'll be able to see that there's a heat sink shaped cavity in the fluid domain. That's how you can ensure that your fluid domain is separated from the heat sink. So this kind of operations that you need to do in order to, and these kinds of operations are called as geometry cleanup operations or prepare operation or repair operation. So anything, it may be anything. So when you have that, once that is completed, we'll directly move on to the meshing part. Okay. Now in meshing, we will basically import our geometry from we basically double click on the mesh at this point, right? So here you can see just let me just go back a bit. Just yeah. So basically here we have our geometry. Once the geometry is done, we are going to move on to the mesh over here. Okay, and do the discretization or do the element by element separation. Then basically we're going to move on to the setup, then solution and results. It's slowly how we are going to move ahead. So in our meshing, in our meshing, what we'll have is first when we have separated all of our components, right? So your simulation software automatically establishes contacts between each of these components. So the one is highlighted in the blue is a contact region, or called as, it is also called as an interface. Okay, so this interface is automatically inserted. The reason is because it needs to establish a boundary where it translates from where simulation software separates from fluid to solid. So when your properties are going to change, pressure, velocity, etc., all of those properties are going to be changing according to this domains. Okay, so essentially when you are doing a fluid flow simulation, your other in this particular simulation, the only term is going to be important in the solid components like heat sink and chip is going to be temperature. Other than that, all the properties are being constant, and like they are not that really important at this instance. So that's sort of things we will be able to establish, and basically we need to consider these terms parameters while simulating. Okay, so these are all the contact regions that we have established. Now once these contact regions are established, we will move on to the mesh. So when you double click on mesh over here, you will see that details of mesh will be displayed over here, and we will be selecting a size factor over here. So all of these things are basically, we are changing the size function being on curvature or proximity, etc. All of those functions are used here to define the based on the actual assembly, right? And basically we are just generating using the default mesh. This is a like 1.147 into e raised to minus, so like basically 0.114 mm or something. So that sort of that's sort of minimum size that we are keeping here. So our minimum element size is going to be that. Now when we are establishing that size, basically you just need to click on mesh and generate mesh. So it will take a bit of time to process the mesh, because it's going to be considering even with this analogies, it's going to be very denser, and will about have like 9,000 like 9 lakh cells. Now just fast forward this part of it. Yeah, so basically this is how your first mesh would look like. This is an unstructured mesh, so I won't be going into details of the element types and stuff like that, but this is how your mesh is going to be. And it's going to be simulation controlled or Ansys controlled, where your softwares will be deciding how the overall flow is going to be, but controls are in our hand. When we ought to control the overall mesh, we can do so by introducing different mesh features called as mesh sizing. In that we'll have edge sizing, body sizing, surface or face sizing. So based on that, each face we can give a separate like separate element count or something. So that way you can these are the different features that are provided to establish manual control and to establish the regions which are more focused as compared to the regions which are not more focused. So that's the general idea. Okay. Now here basically when we have these different section planes, essentially the idea is to just see this is how the overall mesh is going to look like. Okay. And we are just quickly checking the contact regions for that. And this is basically, so that's how easier the mesh generation is going to be. Now one last part, when we are moving forward with the setup, we still haven't defined our boundaries. We still haven't defined our what sort of which is what, like basically what surface is what surface is inlet, what surface is outlet. So all of those things we haven't defined yet. Now we need to define it by using create name selection, by giving it an inlet, by giving this section as an outlet. So all of these names are really important in Ansys, because when you use inlet, outlet, wall, all these names, it's already preloaded in the program that it automatically detects that it's an inlet boundary condition, it's an outlet boundary condition when you are setting up the physics. So there is a less hassle for you. Now when so essentially we have to define these named selections in order for us to tell the software that these are the components we have. So name selection being inlet, outlet, heat sink, fluid domain. So all of those things we need to define. Okay. Now with this, essentially when we are going to move ahead with this, we will just update the mesh over here. Basically the lightning bolt means that it's not updated, and the green tick means it's updated. So when you are moving on to the setup, so basically this is how the setup, let me just fast forward it a bit. So this is how your setup UI will going to be look like. Now in here you'll establish the surfaces, you'll establish the models, etc. So essentially what will happen is you'll be defining first the models that you're going to use. So first you'll turn on the energy equation to establish the temperature factor. Then you will select the turbulence model to define the turbulence for k epsilon scalable warm function. Scalable being that because we can scale this model up to its for a larger domain to understand that to get a good grasp on the properties, because it's a very miniature if you consider its original size, right? So that's why we need to scale it up in order to magnify the effect, in order to magnify the regions of interest and to understand the flows, right? So essentially you are going to establish the materials or defining materials. Then you are going to just go into the cell zone conditions. Basically when you are going to the cell zone conditions, you need to define the environment that chip is going to be. So basically you need to turn on the source terms. Okay, over here you need to ensure that your material is aluminum, then you can actually edit the material over there. So whatever changes that you can make, you have all the freedom in this. Then you will go over the source term. You will click on the source term to establish the energy, right? When you click on the source term, energy tab going to open, and in this you will put a constant parameter for 15,000 watts per meter cube, the energy that we are going to talking about. So at chip is going to generate 15,000 watts per meter cube of heat, and that heat is going to be a source term that is going to be affecting our solution. So that's what we have defined over here. Now, moving on to the other boundary conditions, because other self-zone conditions are don't need any adjustment. So moving on to the boundary conditions, we'll have inlet, where we have established velocity inlet. When you click on outlet, and as you can see over here, they are automatically established altogether. When you click on outlet, the pressure outlet is automatically there. The reason is because we have named the outlet part outlet, or the software only automatically detected, and essentially we need to define the convection term over here, right? So that's how we are going to set up the boundary. So this is a wall fluid domain boundary that we are going to set up for convection, the convection boundary condition. And we have established the heat transfer coefficient for that, temperature for that, wall thickness for that, and that's how we have established. Now, important thing for us to focus on is the contact regions. Okay, so when you are talking about interfaces, here you need to couple those interfaces to actually translate the properties from one point to another point, right? So basically, when you are transferring from solid to fluid, you need to establish that interface, and that's what the contact regions are for, where you can establish mesh interface, where so software knows that I'm moving from a fluid domain to a solid domain. That's where the properties are going to be changing for the material. So all of those things we are establishing over here. And one more thing we need to establish over here, why we are deleting these contact regions that are already established, is because sometimes the auto-generated contact regions or auto-generated mesh interfaces, not contact regions, are going to like there will be a lot of interface options. Like over here, we are going to click coupled wall. The reason is because we are going for a heat transfer problem, a fluid heat transfer problem, conjugate heat transfer. If I'm specifically mentioning, that's why we need to establish this coupled wall, where we have whatever temperature that we have established at the chip, its propagation throughout that from chip to the heat sink, and from heat sink to the fluid domain should be established. So that's where we have to mention it as coupled walls. And when that's done, all of your wall boundaries will be coupled with heat convection and conduction being part of it, whether be based on the boundary. And just okay, we can just pause it for a bit here, and then basically it will establish the overall connection with your solution. Now, moving on to the next part, that is your calculation activities. Now, why do we need to have the CFD? Why do we need to have to export? So basically, while you are moving on to the calculation activities, you have to when you are doing a transient simulation. By the way, we are personally performing a transient simulation over here, not a steady state simulation, just to get the glimpse of time also. So we have also added another variable for our calculation. Now, when you need to export the data, it's easier for us to access in the post processing, where we can save less amount of data than required. Okay, so if you are running for 1,000 iterations, all of those iterations are not going to be useful for you, because every 5 or every 10 iterations, the overall results are going to be more or less same for every 5 or 10 iterations. So in that case, what will happen is basically you can establish your calculation activities, or you can limit the time steps for saving purposes, so that after every 5 time steps, the solution will be saved. And for if you are running it for 1,000 iterations or 1,000, 2,000, 4,000, based on that, the number of iterations that are being saved will be reduced. That's what our requirement is going to be. That's why we are setting this up. And when we are setting up the export, we need to make sure what quantities we want to export, because there are a lot of quantities here mentioned which we don't actually need. We only need the temperature terms, we only need the velocity terms, we only need the pressure terms, right? So all of the other terms we don't really need for observation. right? So that's how we can establish our solution export. And essentially here at the bottom of this screen over here, just, yeah. So over here, the frequency time steps is basically establishing after how many number of time steps we need to save the particular solution. So after here, I have put it after 3 time steps, I'm going to save my solution. And basically you can also change the directory where you want to save it. So you can just save it. After that, you will be moving on to the next part, which is called as initialization. So initialization means that you are establishing your initial guess for the solution. So whatever inputs and whatever the conditions or setup you have done, you would be able to ensure that it is correct. If you have your hybrid initialization being done and it doesn't show any warnings or errors, that means whatever solutions you have set up is correct and it's going in the right direction. One more way to ensure that, based on the convergence criteria, we have usual convergence criteria is about 16, like 15, 16, 10 raised to minus 6, 10 raised to minus 5 in that region. And when your solution turns out, when your initial guess is below like that amount, you would have 10 raised to minus 6, 10 raised to minus 7, right? We will have a good solution. Now here is just we are just calibrating the temperature for the inlet conditions. What we can also calibrate the temperature, what the inlet air temperature should be. So basically we can add any end temperature we want. We have established like it being 282. If we don't establish this, it will just take default temperature that is 300, that is basically 27 degrees Celsius. And apart from that, we can also do other changes for patching the data and stuff like that, right? So here you will have I'm sorry, I'm just going up. It's going to take like 5-10 more minutes for it to complete. But yeah, when we are adding all these terms, right? When we are just establishing the values for the initial temperature at time equal to 0, whatever the temperature is going to be for each of these components, we are just establishing. For a chip, we don't need to establish the initial point temperature because we have already established the source term that the heat term is going to be increased. So in here, we are going to run the simulation for the time step size of 0.001, and we will run for 100 time steps. And the maximum iterations we can have it as like 20 or 45. We can have per time step. We can iterate the solution for each time step for about 20 times, then moving on to the next time step. That's how it's going to be. Now, with this time step, if I multiply this number of time steps to the time step size, it will give me the actual number of actual second duration for which the simulation is going to be. So it's not the actual computation duration, it's the duration for which the actual simulation or the condition is being simulated for. Like air is moving, it is moving over the heat sink for 0 to 0.01 seconds, so something like that. So the overall entire duration of that simulation is going to be 0.1 second. And that's how we are going to simulate it. So this is a very basic condition. This is a very basic simulation, and it usually takes around like 18 to 17 to 18 hours to complete such level of solution. Okay, now we will move on to the solution to understand the results. Okay, first when you go to the results tab, you will have your you need to import your data into the results into this results, because you have exported it. You can directly use the data because you have used a computational export. You have to import it back. If you haven't used the export, it automatically comes, but there is a lot of simulation or a lot of activities involved, right? Now when you need to, okay, just a minute. Okay, when you need to simulate this, when you need to how you are going to observe parameters. So the first thing is you are going to establish some planes in over which you are going to view the entirety of the solution or this thing. Okay, so first thing is first you are going to insert a plane at the right middle section like this, which covers the inlet, outlet, and stuff like that. And in that, you can also establish contours. So by here at the top of the part, there are all these options called vectors, contours, streamlines, and like this, you can insert a contour, right? And here you can select the plane or the surface that you want to establish the controls on. Then you can use the variable, which kind of variable you want to simulate for, like temperature or something. Then you can apply the number of contours you want to have and just click on apply, and you will see that this is the solution. So basically this means that your air is at a lower temperature. This is a temperature contour, by the way. So your air is at a lower temperature. This is your inlet. This is your outlet. Your air is moving from this inlet in this flow manner over this heat sink, and the greener part, the shade that shifts from blue to green to yellow to red, that means your temperatures is getting higher at that instances. Okay, and the around the wall the temperature is high because we have not established any ground for that for those boundaries. We have just established them being like we have just established a certain temperature amount, like 290 or something Kelvin. With that, the overall effect of the chip generating the heat, and the heat is being transferred to the heat sink, it is being transferred to overall domain. You'll be able to view in this manner where you can see that due to the effect of the air blowing over this domain here, is the environment is a bit colder. So your temperature is in the range of 287 Kelvin, 286 Kelvin. So in that range, your temperature is in this like sky blue color region, whereas compared to in your greenish part, you will have a little bit of higher temperatures, 290s, 291. So that sort of regional difference is there. So this is how you can establish the results, which is how you can analyze the results. Now, moving further with the analysis, we'll just see the overall temperature control over the heat sink and how the temperature is different. So you can see over here, like the immediate closest rods of the heat sink to the fluid flow, or to the that are contact with the initial air, have a lesser temperature over there as compared to the back end. So these are the things are also included in, like basically these are the things that are also considered where your velocity will be there as an impact. So if you increase your velocity, probably you will get a much better result throughout these heat sink, where you will have a colder air reaching towards the endpoints, and basically you will have your temperature contours will be dropping down to the sky blue colors or bluish colors, blue shades. Now, with that, essentially, this is how you can simulate, and also you can actually animate this. Basically, you can select time step at 0, go or click on animation, and yeah. So over here, there's this animation option which you can use. There is a probe option which you can check the at exact point, whatever the temperature is. So basically, you can select a point on screen and you can see what temperature it is. So this is the biggest advantage that we have with computational fluid dynamics, where we can actually check the temperature at each and every point in the simulation established. And apart from that, there will be these the simulation ways we can establish the simulation parameters. We can establish the different points at which we want the results to be viewed, and this is how a general simulation setup is done. So yeah, so last part in this, basically we are seeing over here, these are streamlines. So your fluid is okay, let me just. So your fluid is moving from this inlet, is impacted upon these heat sink, and how it's basically behaving throughout this domain is shown over here. And these streamlines are limited to the number of points that we have selected over here. So here we have only selected 25 number of points. So only out of the millions of fluid particles that are involved in this simulation, or that are involved in this domain, 25 of the selected fluid particles we have selected, and basically we are simulating. So basically I've increased the 25 number of simulation 21 number of points to 100 number of points, so that these are the trajectories of 100 fluid particles moving in each of these directions. So this is how you can actually establish the streamlined flows of how the fluid is moving. So still it gives you a clear understanding of how the overall fluid is moving and the overall effects of the of how overall effects of these things are. Last thing I want to mention, like let me just stop it over here. Yeah. Last thing I want to mention over here is towards the end is basically this is just the overall setup that you are doing. Okay, but before all of this, you need to have a calculated way. You need to have a brief understanding of what velocities I am going to simulate this for. Then basically after the simulation is done, you need to establish the parameters, temperature parameters. You need to verify the temperature parameters with either theoretical solution or like experimental solution in order to validate your simulation results, because it's this is just a tool. Its efficiency depends on the user's efficiency or user's experience of the tool. So whatever input conditions that you might put in here, so it doesn't necessarily mean that you are getting the accurate solution. You need to actually rectify these solutions with either theoretical data or experimental data to validate your results. So this is how the simulation, safety simulation validations are being done. But the biggest advantage here is once you have enough experience with CFD simulations, you kind of get the idea of how you're in what range your properties are going to lie, and what range your temperature should be. For instances, at the end of the simulation, with this velocity, I should have my temperature range between so basically, if we are simulating for, let's say, 300 plus degrees temperature, then 300 degrees plus temperature, then basically we should be able to establish that, yeah, my temperature after cooling down, my temperature should be around in the range of 250. And that sort of thing, that sort of analogy you develop, and using that analogy, basically you are reducing your prototyping cost. You're basically reducing your maintenance cost or manufacturing cost for improved design. That's how you are slowly going to progress, and that's how you are going to have that understanding of these concepts. So yeah, with that, I think I will stop sharing. And if you have any questions for me, you can lay away.
Thank you so much, sir, for the knowledge-packed session. I'm very sure that the participants will take back a lot from this workshop. All the topics like heat sink, CFD, pre-processing, solving, and this workbench setup solution, etc. were very nicely explained. Personally, I gained lots of knowledge and learned many new things today from you.
Mhm.
I would like to thank you for such a knowledgeable session.
Yeah.
Now, on behalf of the Mechanical Engineering Society, BIT Sindri, sir, I am honored to present a small token of love and certificate of appreciation before you for
Okay.
spending your precious time among us, taking a workshop on Ansys. Sir, please accept this.
Thank you. Thank you for presenting this to me. One more thing before we go ahead, I would like to share my screen for a brief five more minutes. I'm sure it will not take that much of your time. So I'll just share it quickly, and I just wanted to highlight some parts. Okay. So essentially, when you're doing these CAD simulations, you can get easy access to these sort of knowledge, and the sort of knowledge that I have explained. I have shown you over whatever the resources that I had with me, considering the videos and whatnot. With the internship and courses that we have at Elite Techno Groups, you can get hands-on practice on these concepts. Where in our computational fluid dynamics program, as you can see, we have mastering CFD simulations program. In that program, you would have these basically these programs goals are to establish you and to make you industry ready, make you gain more knowledge and experience in these domains, and like relevant to industry experience, the things that I've mentioned, like how industry works, what sort of things are expected from a fresher's point of view. So all those things you'll be getting an insight upon, and those skills, those exact skills, you'll be getting to learn, you'll be getting to get yourself upskilled with. And with that, you'll have, like, you learn about the essentials of CFD, then hydraulic also, whatever I have explained, it's elaborated further in these. And apart from that, you'll have abundance of projects in this project itself. You're seeing you have about 8 projects displayed over here, but essentially there are a lot more projects involved in these, like many projects to get you familiar with the UI, to get you started with the CFD. And slowly its difficulty level increases with the understanding level as you are moving forward with. You will also learn about the propellers, you will learn about valves, you will learn about centrifugal pumps, electrical panels, coolings, radiator coolings, sedan car drag lift analysis. So all of these like Formula One front wing analysis. So all of these things you'll be able to learn and grow with these parts. Okay. So with that, from ETG's end, also I would like to share my token of appreciation as well, where I will be putting link in the chat box. Let me just, yeah. So this is our website link, and you can use the promo code to avail 20% off on all of the courses that was mentioned on our website. We have not only CFD, we have data science, ML, etc. courses, and apart from that, we have the certification form link for you as well, which delivers a certificate of the attending this workshop, which establishes that whatever you have learned in this workshop, you will be able to showcase that over LinkedIn, and you will be able to add that in your resumes. So more about that at a later part, where you can register, where you can go website, check out, and see for yourself like how you can upskill yourself. So yeah.
Thank you, sir, for being such a help to us. Now the participants can ask their queries in the chat box or may raise their hand.
Sure.
So we have some questions in the chat box.
Sure.
So the first question goes, which subjects are the most must to have command in for the working in analysis softwares?
Okay, so essentially you need to have command on computer like fluid dynamics, heat transfer, and apart from that, like if you are going for structural mechanics or structural analysis, there are two kinds of separate analysis involved. One is structural, one is fluid. So the fluid part covers in turbo machineries or fluid mechanics in general, and apart from that, thermodynamics and heat transfer formulations are associated with it. But if you go for structural analysis, there comes your mechanics part, where there comes your solids, theories of failures, and theories of machines. Those parts of things you need to have a strong brief knowledge about, like strength of materials and those design of machine elements. Those sort of subjects you need to be have a strong background knowledge. Yeah,
Thank you, sir.
I hope answered that question.
Yes, sir. So the next question goes, so can we say CFD is the way of modifying heat sink virtually?
Yes, definitely. So how we can do is basically what we can do is we can try different configurations. So when with the configuration that I have shown you over here, very pattern kind of way, like it's very streamlined way. Based on the randomized structure of those rods that you saw, you can establish a significant pattern from your end, which facilitates the airflow through the gaps between these rods, which can efficiently make the air accessible throughout the heatsink. So that sort of configurations we can modify. We can test it for different simulations by using such similar conditions and see actual exact implementation from the past results. So you can actually see the improvements in temperature or degradation in the temperatures in that sort of things. So this is how you can, this is a very trial and error method. When you are starting with it, you have to be trial and error way. Your approach has to be trial and error way. But as you move ahead, you will have that fundamental understanding growing with you. With enough experience, you will have that baseline understanding where with by just looking at a particular simulation, you will be able to just tell that this particular simulation is a good simulation or a bad simulation, or whatever the changes or modifications that will be needed, you'll be able to establish that. So that essentially comes with knowledge and experience. So the more you practice, the more you grow.
Sure, sir. So the next question goes, what is hyper meshing in the workbench? Is it different from the one you showed?
Hyper meshing is not a concept. Hyper mesh is although a software, is a tool which is provided by another software providing company called Altair. So hyper mesh is usually used in industries for where it is heavily associated with there are going to be a lot more components. So here the components that I'm showing you are only 3 components. Like one is being fluid domain, apart from the solid components. But when you are actually moving into the industry, there are hundreds of components involved in a single component. Like if you are talking about compressible pump itself, there's volume, casing, nuts, bolts, all of those things, like all of the miniature components are going to be there. So for each and every part, you need to have a constructive meshing. You need to focus on the localized regions, and for that, hypermesh is being used for meshing purposes only. That is a tool. It's not a hypermeshing. It's not a concept. So yeah.
Thank you, sir. Your doubts, they got their answers very clear. I would request the participants that if they have any query, they may ask in the chat box.
The biggest thing with this is you need to understand and you need to learn about, explore about these concepts. Basically, the area of interest, CFD is a very vast domain. Based on your smallest area of interest, based on that, you need to move ahead forward with. So this comes with a lot of practice. So to get you started with, you can try this simulation. Just take a pipe, simple pipe, and simulate it with a certain velocity, like 10 meters per second or whatever feasible velocity with a default mesh. If you have access to the Ansys tool or Ansys student version, it's easily available on Ansys website, official website. You can just download it, you can install it, and use it for 1 year of your academics throughout that, and then the license can be renewed for the next year when the next version comes. So it's very readily available. You can use that to practice and just simulate this concept and just see whether your flow is being laminar, moving, whether your fluid is moving through the pipe is being laminar flow or turbulent flow. Just see that. So this is a simple turbulence model that I suggest to everyone to get you started off with.
Thank you, sir. Thank you very much for being with us. Thank you for this enlightening session. We were very obliged to have you with us. I think we are done with the queries.
Yes.
So,
yes.
Coming to the awaited announcement for all the participants present here. Mechanical Engineering Society BIT Sindri presents you Shastra 2022, an opportunity for you to acquire the right skills and test your knowledge to overcome the obstacles on your way. It is being organized to test your performance of your analytical mind in a competitive, time-constrained environment. So grab this opportunity to win internships as well as exciting prizes worth 40K plus. For more details regarding competition, you can visit our website www.mes.bitsindri.com or check out our social media handles. Thank you.
Thank you. Thank you for lovely participants. Thank you for attending the session. Have a nice evening, everyone, and have a nice week. Keep learning, keep exploring, share what you know, explore the knowledge, and be better. Have a nice evening, everyone. Bye-bye.
Thank you,
Thank you,
sir.
sir. Thank you so much.
You're welcome.